Hello everyone, happy Monday. We're talking about estimating a population mean today. So we are going forward with our lesson on confidence intervals, but now we're starting with some numeric data. So let's go through this. The activity is how much does an Oreo weigh? Let's say that I want to investigate the average weight of an Oreo cookie to determine if the average weight was less than advertised. I select a random sample of 30 cookies and found that the weight of each cookie in grams. I found that the mean of my sample was 11.1921 grams and standard deviation 0.0817. I'm going to make a 95% confidence interval to estimate the true mean weight of an Oreo. All right, so let's do this. First things first, we should recognize that this is numeric data because we're talking about the average weight, and we have a numeric value for that mean, okay? So when it comes to the point estimate is X bar, which is 11.1921. The population of interest would be all Oreos. And the parameter for X bar would be mu, the true mean weight of an Oreo. Okay, the sample was my 30 Oreos. And the statistic is X bar, that equals 11.1921. And this was the sample mean of 30. Sample mean weight of 30. Okay, was a sample a random sample? It was stated. Why is this important? Same as last time. Generalization. Representation of the population. All right, let's keep on going. What's the formula for calculating the standard deviation of the sampling distribution of X bar? All right, so remember what we do is we take the standard deviation and we divide it by the square root of n. So this would be sigma over square root n. All right, and let's keep going on. It says what condition must be met to use this formula? Has it been met? Remember right here, this is your 10% condition. And all of this should be feeling pretty familiar. Very similar to proportions, right? Yes, it has been met. We're going to assume 30 is less than or equal to 10% of all Oreos, okay? And that's a safe assumption to make. All right, in the formula for standard deviation of the sampling distribution, we don't know the value of sigma because if we did, we would have also known mu and we would not be making a confidence interval. So just like with proportions, we're going to use the standard error. The standard error of the sampling distribution looks like the standard deviation, but instead of the standard deviation of the population, we have to use that standard deviation from the sample, S of X bar over root n. So we're going to take 0.08 and put it over square root of 36 and get 0.0146. So that's our standard error that we're going to use for our confidence interval. All right, let's keep going. Would it be appropriate to use a normal distribution model to sampling the distribution of X bar? Justify your answer. In this case, yes. 30 is greater than or equal to 30 by the central limit theorem. So the distribution is approximately normal. All right. All right, number 8. So here's a little difference from proportions to means. When finding the margin of error for a confidence interval for a proportion, we use that critical value z star. For a mean, we use a critical value called t. or T star. Why is that? That's because to take into account the fact that we're using only sample data, we're using sample data for S sub x and for that standard error, and we're approximating, we use a distribution that has a little bit more variation than the normal distribution. So for instance, if the normal distribution was centered at mu with standard deviation sigma over root n, the normal sampling distribution, we are used to getting a normal x bar value and finding that area under the curve. That's perfectly fine. Okay, that distribution is just a little bit more compact than the t distribution, which is a little bit more spread out and takes into account that there's more variation in the sample than there is in the population. And since we're not using the population data, the distribution is just has more variation and it's more spread out. So instead of using what we would think, which would be a z-score, which we're used to, x bar minus mu over sigma over the root n, since we're replacing that sigma with sampling data, S, we replace Z with T, just because this introduces much more variation into the mix than the normal distribution would, okay? So on that T distribution, you have, T star values or T scores, they can be called, and you can calculate your T score using the x bar minus mu divided by S over root n. Okay, let's go to the next page. So one thing that we need to talk about is how we calculate a T star. It says, what T star is needed for this confidence interval? Use table B. We're actually going to use our calculators, okay? The degrees of freedom is instead of using for a normal distribution, we use mean 0, standard deviation 1. For that T distribution, we use mean 0 or whatever it is for that particular scenario, and then we use the degrees of freedom, which are n minus 1, okay? So let's look this up. The degrees of freedom in this case are going to be 30 minus 1. And instead of using inverse norm, we're going to use inverse t on our calculator, okay? We're going to do the area to the left, and then we're going to do the degrees of freedom. So for a 95% confidence interval, that means we've got 5% on the outside, 2.5% in each tail. We're going to put the degrees of, the area to the left, 0.025, and degrees of freedom, 29. And calculate, and you should get a T star of 2.045 approximately. Okay, inverse T is right underneath inverse norm in your calculator. Now let's calculate the margin of error. Remember, your margin of error is equal to the critical value times that standard error. So our margin of error is our critical value, 2.045, times our standard error, 0.0146, and that's 0.03 approximately. All right, let's keep going. Let's calculate that confidence interval. So we're going to take our point estimate from the front side, which was 11.19, that sample mean, plus or minus our margin of error, 0.03, and our confidence interval is 11.16 to 11.22. So let's go ahead and interpret the interval. We are 95% confident that the interval from 11.16 to 11.22 captures the true mean weight of all Oreo cookies. Write a specific formula for the confidence interval for a population mean. All right, perfect. Point estimate, x bar, plus or minus our critical value, t star, times standard error, s of x bar over root n. Sometimes this is just s, not necessarily with that x bar. Either way is okay. According to Nabisco, an Oreo weighs 11.3 grams. Does our confidence interval provide convincing evidence that the true average weight is less than 11.3 grams? So we have our interval from 11.16 to 11.22. Our confidence interval does not include that 11.3, okay? 11.3 is not within the interval. So this suggests the true weight is lower. We're not so sure if they're telling the truth. We're 95% confident that the true average weight is between those values, and 11.3 is higher than that. So we're not thinking that's truthful. All right, so let's just talk about some notes here. All right, so the conditions are kind of the same as they've always been. We need a random sample. Condition number 1. Condition number 2, we need normality. The only thing is that there's 3 ways to meet normality when it comes to numeric data, okay? And we're gonna list them all out in order, the order that you kind of wanna approach them. First things first is if the population is stated normal, then the distribution is approximately normal. Number 2, by CLT, if n is greater than or equal to 30, okay? And you have to state that. And the distribution is approximately normal. And last but not least, we have another option here, and that is that the sampling data shows no strong skew or outliers. So if we have the raw data, we can look at the data and see if it looks good. And one of those options is a normality plot. If you remember, if that normality plot is approximately linear with no crazy outliers, then the distribution is approximately normal. So 3 options for normality when it comes to numeric data, okay? And then our third thing we have to check is that 10% condition. Okay? And that's our independence, right? When we're sampling without replacement. All right, so why T star instead of Z star? To account for that variation. When using sample data only. Okay. Z star, proportions. T star, numeric. Actually, I'm going to write this differently. means. So this is categorical, this is numeric. Okay? For your T star, the degrees of freedom are equal to n minus 1 always. Okay? Your calculator pathway here, you use inverse T. And you use the percent area to the left. And degrees of freedom. There's also, if you wanted to find the area underneath a T distribution, you could use TCDF the same way as we use normal CDF. You got lower bound, upper bound, the mean, and then the degrees of freedom. Okay? And that's pretty much it for confidence intervals in regards to means. You tried number 1 and 2 on your U-Try. If you want to use table B to read your T-star values, you definitely can. That's an option. Just if you use table A for Z-scores, you can use table B as well. And if your degrees of freedom are not on the table, round down. You'll see what I'm talking about if you go look at it. You can always use that table to find the degrees of freedom as well. All right, so go ahead and try number 1 and number 2. Pause this, then check your answers. Okie dokie, and go ahead and check your answers. And that's it for today. I hope you have a wonderful day. Go get some Oreos. Bye.